Hello, everyone. Here's Zhimin Wang from my app. Here, I will try to update you about the JUNO Detector design and status on behalf of JUNO collaboration. So, first, try to remind you about what's JUNO and update few about the detector and the physics of JUNO. And final, we update you the current status and the progress of the JUNO civil construction and the detector components production and the final installation. So as you know, JUNO, Jiangmen Underground Neutrino Observatory, is located in the southern of China, Guangdong Province, Jiangmen City, and nearby the Macau and Hong Kong. Also, Diabei equivalent location. And JUNO located two nearby reactor cores, Yangjiang, which contains 6 reactor cores, and Taishan now 2 cores. And JUNO designed with the excellent energy resolution with huge liquid scintillator target volume. You can see here, which can reach around 3% divided by square E. And comparing to Diabei, Boxino, and Camland, JUNO has the largest 20 kiloton liquid scintillator as target, and can reach the photocancelled coverage to 78% with high QE PMTs. And the final effective light yield can reach around 1300. That make the JUNO energy resolution can reach around 3%. Yeah, as we side. And finally, also the energy recalibration ability can reach by the 1%. And the JUNO detector system located and on the ground, around 700 meters over burden, and itself in the Pisa Tower scale. And its key critical part is the central detector, contains the critical sphere with diameter of 35 meters, and contains the 20 kiloton liquid scintillator, and it's supported by a steel structure. And the steel structure diameter is 40 meters. And the PMTs, 18,020 inch and 26,000 3-inch installed on the steel structures, and to make the 78% coverage. And to make the 20-inch PMT working correctly, there has 2 coil systems to shielding the Earth's magnetic shielding. And also the central dipped in pure water pool contains 35 kiloton water, and computed equipped with 2,400 KQ PMT2. And at the top of the water pool, there has another top checker to do the precise measurement of the muon tracking, and also the calibration house there. And here is current joint collaboration. Now totally has 665 members from 77 institutes all over the world. You can see here. And here also show you 2 photographs, the previously face-to-face and the latest online meetings too, as our this meeting. And JUNO physics. The primary goal of JUNO is the neutrino mass ordering, as you know, and as by the precise measuring the energy spectrum by structure of the neutrino reactor neutrinos energy spectrum, and also can precise measurement the neutrino mixing parameters, most of them by than 1%. And at the same time, also can addressing many important topics in neutrino and astroparticle physics. For example, supernova neutrino, DSNB, and some neutrino at atmospheric neutrino and geoneutrino. And also we preliminarily calculated the event rate for each of them. And also there has another 2 parallel talks in the parallel mission session for JUNO related physics. For more detail, you can go there and have the more reference. And concerning the reactor neutrino detection of JUNO the ABD events, so we already checked the video showing the energy and the timing cut, the mu-veto related efficiency. The final combined efficiency around 73%, and can reach provide the around 60 neutrino rate per day. And also checked the background, including the geoneutrino accidental background and the cosmic ray related background too. And also concerning and comparing to the JUNO Yellow Book results published in 2016. Today, we have a few key updates on the released items, and all of them accepted by the PPMP paper. So two weakness is that, again, we already talked about that only 2 of Taishan reactor costs comparing the previously 4. So that means another 25 neutrino at flux reduced. And the experimental Hall shifted up by 6 meters. That will generate another 30% higher muon flux. But at the same time, we optimized the neutrino selections. For example, the minimized that time of muon veto, which makes the improve the live time from 83 to 93% with similar background level. And we have higher 20 into PMT for the detection efficiency from the proposed 27 to the current merit 29%. We will see more detail. And also we have more realistic PMT and linear optical model, which all both generate better understanding and can somehow balance to the negative point there. And we will can have better understanding of the energy non-linearity model and can do the combined analysis of tau and JUNO detectors. So we will see more detail on the tau detector. And concerning the JUNO central detector, as we discussed, is the critical part of JUNO. The concern includes the acrylic sphere contained by 260 panels and the supporting structure. And here you can see the thermal forming of the acrylic panel with 12 centimeter thickness and 3 times 8 meters. And here it shows the recently transportation testing of the panel. And this is the latest panel motioning and node bonding and the pre-location of the top part of the acrylic sphere. Yeah, you can, everything is on its location, good way. And all the acrylic sphere panels can reach 1 ppt background level. And concerning the installation of central detector, there has a detailed proposal of that. The basic idea is to do the installation from top to bottom on a platform and with some self-lifting structure for each layer. You can see here we already have some testing of the self-lifting that. And also the platform is done by the platform with some cartoon on there. And here the platform also already pre-assembled in factory. You can see here, and the acrylic sphere also tested by the with the platform there. And the platform supporting legs already some anchors installed at the bottom of the water pool. Here is the stainless steel structure, and including the arm structure and the legs and the anchors, and all the arm produced and they will be transported to the capping site. And the top part of the structure and the legs, supporting legs, welded and produced, and the anchors are embedded in the bottom of the water pool too. Concerning the PMTs, as you know, there has 2 sides of PMTs will be used in JUNO to reach the 78% coverage, including 18,020 PMTs for central detector, which have around 75% coverage, and another 2,400 used for the veto detector. And there, and from with 5,000 from HPK dynamic PMT, another 15,000 is from the newly developed NVTMC PMT. Now all of them delivered and qualified. And the measured average PDE is on 29% for central detector. Our proposal previously is 27. Yeah. And the 26,300 PMT already finished the production and tested. And the waterproof reporting for the 20 PMT already finished this month, actually last month. And the improvement protection structure of the 20 PMT is the production and assembly phase. And also another thing need to remind you is that with the PDE measurement system has a little bit aging. And I'll consider that the correction later will have a little bit higher of this one too further. And as we discussed, the Veto system of JUNO composed by water chunk detector and top tracker. The water chunk detector will shield the radioactivity of CD. And the final design fast neutral background around 0.1 event per day. And the water pool contains 35 kiloton pure water with circulation system, as you see here, the circulation calculated. And the design rate now is updated to less than 10 milli background per cubic meter, better than the yellow book. And also the thermal uniformity calculated, with the detector will running around 21 centigrade environment, water temperature. And the muon efficiency design higher than 99%. And the top tracker aiming the precise muon tracking covers 1/3 of all the muons passing through the central detector, and which renews from Opera experiment. And the electron is already updated for higher reactivity. And top detector will located at the Taishan Anti-Radiation Observatory, a satellite experiment of JUNO will located around 30 meters far away from a Taishan reactor core, and around 10 meter background underground, with 2,000 ABD per day for precise measurement of reactor neutrino spectrum, and also provide a model-dependent reference spectrum for JUNO. And the detector designed with DDRS, running under -50 centigrade, and around with around 10 square meter silicon PM with high PD higher than 50 and coverage 90%. The effective light yield around 4,500 per MeV, and the resolution aiming to around 2% divided by square E. The 1-to-1 prototype is under construction at AHAB without full silicon PM. The top detector aiming to next year running. And here, showing the latest status of the JUNO site. Here's the surface building. You can most of them already on location. And the 5,000 ton liquid incinerator tank ready. And the facility utility is ready. Here's the computing room. And the ventilation pipe and equipment installation also in progress. Here's the entrance of the tunnel. And show you some photographs of the water pool. Here's the bottom view of the water pool. And this is the transportation tunnel. Here is the border view of the water pool. Yeah. And here is the border view with crane lighted and water lining finished, the latest one. And then now JUNO proposed 2014. Until this year, even we have some delay, so electronics protection started now, and civil construction almost finished now, and technical installation begins. And we plan to finish the installation next year and start feeding and testing. So quick summary. So JUNO has a vast program in particle physics and astrophysics, and trying to probing the neutrino oscillation mechanism and with a good precision. And we update you the reactor and detector design, few of them, and the water pool can finish the construction, and the detector components production assembly installation going on smoothly. And we plan to finish next year. And there, as we mentioned, so there is two another parallel talks for JUNO paraphysics and another 4 posters for JUNO detector. You can go there for more detail. And thank you for your attention.